Hey everyone, we're going to talk about continuous probability distributions. Again, this is going to be an abridged version of the chapter. We're really only going to talk about one of the two. For example, there's going to be another one called uniform probability distribution that we're going to gloss over now, but and focus on the normal distribution. But anyway, let's kind of jump into it. So let's talk about this normal probability distribution. The normal probability distribution is a continuous distribution with the following characteristics. Before I start on the characteristics, let's just talk about continuous data. Anything that can be, again, further subdivided and still make sense. So for example, how old you are can be continually divided. How long it takes you to walk to school can always be divided. Time is a really great example of a continuous variable, but height is another one, right? You can people have all sorts of variety of height, and you can get really, really granular with your measurements. Ultimately, people kind of stop at inches, but you can further divide inches and have it still make sense. So height would be another good example of a continuous distribution. Further, height is a good example of a normal distribution. So height should be something that you're thinking about as you think about these sorts of things. So first, the normal distribution is bell-shaped and has a single peak at the center. So for example, that's kind of leads into the second point here. It's symmetric. So you have this single peak at the middle, and you have tails. It looks like a hill, and it kind of trails off and then gets really flat towards the ends. And when I say gets really flat towards the end, I mean this third point by it's asymptotic, meaning that the curve approaches but never touches the x-axis. So it gets really, really close to zero, but doesn't actually ever hit it. Zero as in the y-axis. So it gets really close to zero, but never touches it. It kind of keeps on going forever. So you can have an infinite value on your x-axis, positive or negative. And then finally, it's completely described by its mean and standard deviation. So I'm going to talk about this a little bit more in a second, but this is an important note. So if you know the mean and you know the standard deviation of some distribution, and you're given the information that it's normally distributed, then you know everything about that distribution. You know all probabilities, you know everything, because we have ways of finding this stuff out. So because of this, there's going to be a family of normal distributions, and they're going to be all described by their mean and standard deviation. So here's what a normal distribution looks like. Let's think about this in terms of height. So the average height would be right in the middle. There are people who are taller and people that are shorter. Because it's symmetric, you have an equal number of people who are both taller than average and shorter than average. You can have people, because this is theoretically asymptotic, you can have people of as tall as possible. Of course, this is going to be really, really, really unlikely because this is going to be so asymptotic, right? This is so unlikely to find somebody who's 8 feet tall. But there have been the occasional people you see online or something like this that do exist and are indeed that tall. Similarly, you're going to have the other extreme where people can be infinitely short. Of course, there's going to be a natural bound at zero. In fact, it's going to be much higher than zero, but zero is literally a pretty concrete bound for height. You can have negative height. But for all intents and purposes, height approximates a normal distribution. So you have these two halves. You have the mean, the median, and the mode are all equivalent. And you have, this bell-shaped curve being the normal distribution. So talking a little bit about how I had mentioned before that there's a family of normal distributions. This is kind of what I'm talking about. So this bottom picture, you have different, the same curve, but just with different means, right? So the same standard deviations of 1.6 grams. So the dispersion is exactly the same, but the mean is a little bit different. So the mean is going to be spread out, kind of swinging moving the distributions horizontally along the x-axis. On the picture here in the top left, we have the same average, all have an average of 20, but different standard deviations. So the larger the standard deviation, the flatter the curve, right? The peak kind of gets pushed down and the tails kind of get pushed up and out. So this would be the largest standard deviation and this would be the smallest standard deviation. And then finally, which is much more likely in the real world, is you have different means and different standard deviations. So you have this right here. So one thing that's a really salient example, at least I think to undergrads, is SAT and ACT test scores. So the SAT, at least when I took it, and I think it's different now, but I'm just going to talk about my experience, was out of 2,400. And the mean was defined and all that stuff. And the ACT was out of 36. Now, it's really important to put your best foot forward when you're applying to colleges. So you want to make sure that you're submitting the best score possible. So you have to figure out like, which exam did I do better on? Well, it's not really quote unquote right to just kind of like look at your score and divide it by the total possible, because you know that going from a 35 to a 36 is much more unlikely than going from a 27 to a 28. So you have these two distributions. One of them, the SAT, has a very, very high average relative to the ACT, but also a very, very large standard deviation, right? Standard deviation could be like 400 points or something like this. Whereas the ACT has a much smaller average, of course, and a much smaller variance. So what you need to do is you need to figure out a way to compare these two things. Well, the first thing you can do is you can take all of the scores and center them. So you can center both the SAT and the ACT scores. How would you do this? Well, I'm going to take every single score and I'm going to subtract off the average. So for all the SAT scores, I'm going to subtract off the average one. And now the average is going to be at 0 with this large standard deviation. So you can still think of these distributions now on the same X point, right? Because they're both going to be kind of looking like this one here. They start here, but because I'm subtracting off the averages, they're going to shift over and now they're going to look like this, where instead of the average being 20, the average is going to be 0, right? Because I'm taking away the average. Then from here, what I want to do is I want to scale them such that their variances are equal. So a 1 unit change or a let's call it standard deviation change, is equal for both, right? So we can actually compare both of these things and see how far away we are from the average. So what I'm going to do that is I'm just going to divide by the standard deviation. And when we divide by the standard deviation, we're going to force it such that each of these distributions are going to look more like this, but they're all going to be centered and on top of each other. So they're going to have the same variance as well as have the same centers. So the way we do this is called the z-value. What we do is we say this is going to be the distance from a selected value from the mean in terms of the number of standard deviations. So if we get a z-value of 1.5, this means that we are 1.5 standard deviations away from the mean. This is a really important concept that you'll talk about pretty much for the rest of the course. When you start to talk about regression analysis, z-values come up over and over and over again. And we'll talk about the significance of z-values when we talk about the central limit theorem in the next chapter. But essentially, once you have a z-value, you're converting your distribution that's completely characterized by the mean and the variance, and you're scaling it such that the variance and the mean are now 1 and 0 respectively. In other words, you have a distribution with a mean of 0, so they're all every single distribution is now centered at 0, and now you've collapsed all of the distributions such that the variance is going to be equal to 1 because you're dividing, or sorry, the standard deviation is going to be equal to 1 because you're dividing all of these numbers by the standard deviation. So now you have the SAT and the ACT having the same mean and the same standard deviation. And now you can compare the Z value for whatever SAT score you got and the Z value for whatever ACT score you got. And you can figure out which one am I farther away from the mean, right? Hopefully in the positive direction. In the negative direction, you'd want to be closer to the mean, right? Because you want to be closer to average than farther from average. But essentially is now doing this math, you'd be able to very easily tell which score did I do better or which exam did I do better on. So you can also find probabilities, right? So here's an example of a z-table that I'll kind of gloss through quickly, but pretty much once you get a z-value, you can start to do probabilities. So you know that half the distribution is going to be 50%. And then according to some z-table, you'll be able to calculate the probability of anything between 0 and 1. Similarly, you'll be able to kind of manipulate this using I'm using air quotes here, geometry, as well as algebra. So there's different examples here. I'll kind of flip through them slowly so you guys can pause the video and take a look at them as you want. Okay, and then I'll end the video here and keep going to the next chapter.